Welcome to Understand the Math. In this problem, we're given a matrix A, and it's a 3 by 3 matrix, and we're asked to find two things. We're asked to find the eigenvalues of this matrix, and then we're asked to find a basis and geometric description for each eigenspace of matrix A. Let me tell you exactly how we're going to do this. To find the eigenvalues, we're going to solve the equation determinant A minus lambda I is equal to 0 for our eigenvalue lambda. To find the eigenspaces, we're going to put A minus lambda I in a matrix and augment it with 0, and then we're going to put that matrix in reduced echelon form and find X for each lambda. That's going to take a little bit of time. Let's go ahead and let's start by finding the eigenvalues. So for part A, we're going to start by taking determinant A minus lambda I equal to 0. We have the determinant of 6 minus lambda minus 2, 2. So we're basically just subtracting lambda off the main diagonal. That's what it means when we have A minus lambda I. And then we have a 3, a minus 3, and 7 minus lambda. And we're going to set that equal to 0. We're going to solve this by using cofactor expansion. I think that's the easiest because notice that in our second column, we only have one entry. So it won't take too much time to do this. Let's go ahead and let's circle this because that's our non-zero entry. So to find the value of this determinant, we're going to have a sign factor times this entry times what remains when we cross out the row and column common to that entry. So let's do our sign factor first. Our sign factor is a plus. You start in the upper left-hand corner, and then you work your way over, plus, minus, plus. We could have gone down and then over, and we would have gotten the same thing. The sign pattern just alternates with plus and minus. So our determinant is equal to plus times 4 minus lambda times the 2 by 2 determinant that's left, and that's a 6 minus lambda, a 3, a 2, and a 7 minus lambda, and we're going to set that equal to 0. So we have 4 minus lambda, and then in this determinant, we're going to evaluate the determinant by multiplying the main diagonal and subtracting off the off diagonal. So this is going to give us 6 minus lambda times 7 minus lambda minus 2 times 3, which is 6. I always tell my students, when you get to this point, you have to be very, very careful not to just start multiplying everything out. Because if you do that, you're going to end up with a cubic equation that's going to be really hard to factor. So what you want to do instead is just put this in your pocket for a minute, and then let's work on simplifying this part. So we have a 4 minus lambda, and then in this middle part, we're going to have a lambda squared minus a 7 lambda minus a 6 lambda, so that's a minus 13 lambda, and then we have a 42 minus a 6, and that's equal to 0. So we're going to simplify that inside, and we end up with a lambda squared minus 13 lambda, and then a 42 minus 6 gives us a 36. Notice that 4 times 9 is 36, and that also adds to 13, so we can easily factor this as lambda minus 9, and then a lambda minus 4. And see what happened by holding on to this term, we ended up factoring the entire cubic equation. This gives us eigenvalues of lambda is 9, and 4, and 4. Sometimes you can also write this as lambda is equal to 9, 4, and then in parentheses, you can write down multiplicity 2. Either way is usually fine. Okay, so let's go back up. We found the eigenvalues of matrix A. So let's go ahead and let's highlight these. We have 9, 4, and 4. Now what we have to do is find a basis and geometric description for each eigenspace of matrix A. I'm going to start by finding the basis associated with our eigenvalue lambda is equal to 4. So what we're going to do is we're going to take A minus lambda I, we're going to augment it with 0, and we're going to put it all the way down to reduced echelon form. So let's go ahead and do that. What we're going to do is we're going to have our matrix A, and we're going to subtract 4 off the main diagonal. So let me go back up here and we'll highlight this. There's our main diagonal. So we're going to subtract 4 off it. So we get a 2 minus 2, 2, 0, 0, 0, and then a 3, a minus 3, and a 3. Let's write that down. We have a 2, a minus 2, and a 2. We have a column of zeros, and then a 3, a minus 3, and a 3, and we're going to augment it with 0. Let's go ahead and circle our first pivot, and this is really nice. Notice that our second row and our third row are multiples of our first row, so those rows are just going to go to 0, and we can do a scaling on our first row and divide it by 2, so we get this matrix, 1, 0, 3 halves, augmented with 0, and then everything else is equal to 0, which is quite nice. Now, to find our eigenvector, we're going to circle our pivot, and we're going to solve for that pivot. So this is x1 plus 3 halves x3 is 0, which gives us that x1 is minus 3 halves times x3. Let's go ahead and let's form our vector x. There are 3 columns in A, so we have 3 entries in x. So we have x1, x2, x3. And then let's plug in. We have x1 is minus 3 halves x3. And now we have to figure out what to do with x2 and x3. Let me make a note up here that because these columns are missing a pivot, that means that x2 and x3 are free variables. So when you put them into your matrix, they just go in as themselves. So this is an x2 and that's an x3. Now what we have to do is split our vector apart. We can pull out an x2 and that's going to multiply 0, 1, 0. And then we'll pull out an x3. And for that one, we're going to have a minus 3 halves, a 0, and a 1. And our question asks us to find a basis for the eigenspace. So the basis is going to contain these 2 vectors. And I'm looking for some free space. Let's see if we can squish it down here. So let's just write down basis equals, it's going to contain our first vector, 0, 1, 0, and then our second vector, minus 3 halves, 0, and 1. And that's the basis for the eigenspace corresponding to our eigenvalue lambda is equal to 4. Now, let's think about the geometric description. We have 2 vectors in it, so that means it's going to be a plane, and each vector is an element of R3. So our geometric description of our basis is that it's a plane in R3. Okay, we got that one done. Now I'm going to flip the page, and we're going to find the eigenspace corresponding to our eigenvalue lambda is equal to 9. I went ahead and I wrote down our matrix A just so we wouldn't have to flip back and forth between pages. So let's write down lambda is equal to 9. And we're going to begin just like we did before. We're going to take A minus lambda I, and we're going to augment it with 0. So for this one, let me go ahead and let's highlight our diagonal. We are going to subtract 9 off of our diagonal. So we're going to get a -3, a -2, and a 2, and then a 0. 4 minus 9 is a -5, and then a 0, and then a 3, -3, and then 7 minus 9, which is a -2. This one is a little bit harder than the other one to simplify. Okay, so the first thing I would like to do is do some scaling because I'm looking at this row, and we can make those a lot simpler. So I'm going to take row 1, and I'm going to change it to row 1 divided by -3. That's just doing a scaling. And then row 3, we're going to let be row 3 divided by 2. And this is going to give us a 1, 0, -1 on our first row. Our second row is going to stay the same. And then our last row is going to be a 1, 0, -1. Let me change that 0. It looked like a 6. There we go. Now we're all set. Let's go ahead and let's circle our first pivot. And we're going to proceed to get a 0 below that. All those entries are going to become 0. So we're going to take row 2, and we're going to replace it with row 2 plus 2 times row 1. And then we're going to take row 3, and we're going to replace it with row 3 minus row 1. Give ourselves a little bit more space. And here's what we get. The first row stays the same. And then we're going to multiply our top row by 2 and add it to our second row. So we're going to pick up a 0. The -5 stays. And then we're going to have a -2 minus 3 gives us a -5 and then a 0. And then we're going to take -1 times our first row and add it to our third row. So we get a 0, 0. And then we have a 1 minus 1, which is 0. Oh, that's nice. That row is all zeros. So we're almost done. Let's go ahead and let's circle our pivot here. To put our matrix in reduced echelon form, all of our pivots have to equal 1. So we're just going to take row 2, and we're going to replace it with row 2 divided by -5. Our top row is 1, 0, -1, augmented with 0, and then we have a 0, 1, 1, 0, and then our last row is zeros. So our matrix is now in reduced echelon form. I'm going to circle the pivots because those are the variables that we're going to solve for. We have x1 minus x3 is 0. So that tells us that x1 is equal to x3. And then we have x2 plus x3 is 0. So that tells us that x2 is equal to minus x3. And then let's just make a note that x3 is a free variable, because there's no pivot in that column. Now we're going to form our vector x. It's equal to x1, x2, and x3. We're going to plug in what we just got for x1 and x2. So we have an x3, a minus x3, and another x3. And let's pull the x3 out front. And we get a vector 1, minus 1, 1. So our basis for our eigenspace corresponding to our eigenvalue lambda is equal to 9 contains the vector 1, minus 1, 1. And then lastly, let's talk about the geometric description. Our basis contains one vector. So our geometric description of our basis is that it's going to be a line, and our vector is an element of R3. So we're going to have a line in R3.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.